I'm going to go through the answers here to the Unit 7 practice test. So let's get some space. So in the beginning here, we're just looking at this situation. Here is our equilibrium, and we're deciding, okay, is it going to shift to the right, is it going to shift to the left, or is it going to not shift at all? And we'll choose those answers. So a catalyst is added. Okay, catalyst is added. We know that there is no shift. All it is that it gets to the same equilibrium more quickly. NO2 gas is removed. Okay, so here it is a product. We're removing it. The stress is there's not enough NO2, so it's going to shift to the right in order to replace the stuff we take away. NH4NO3, that is a solid. Okay, if we solid, there is no shift. Okay, if you add or remove a solid, it does not shift the equilibrium. The pressure is increased by decreasing the volume. Okay, the stress is there's not enough room. Well, this side has 0 moles of gas, this side has 3 moles of gas. If there's not enough room, it's going to shift to the side with fewer moles of gas, so it's going to shift to the left. And the temperature is increased, it means there's too much heat. Too much heat is going to shift to the left to use up that heat. Okay, multiple choice. For this reaction, okay, the conditions that would shift the equilibrium to the right, so who's going to shift to the right? Okay, we notice that heat's over here. We notice that we have 1, 2, 3, 4 moles of gas and 2 moles of gas. Okay, high temperature, high pressure, high temperature, pressure unimportant. Okay, we're talking about pressure and temperature. Well, the temperature, okay, here's heat, and on this side, if I can shift to the right, it's because I need more heat. So if I lower the temperature, that would shift it to the right. If I increase the temperature, it'd be too much heat, shift to the left. So we want to get rid of the high temperature answers. So that's not the answer, that's not the answer, and that's not the answer. Okay, then if I want to get it to shift to the right, this has fewer moles of gas, so that means I need to squeeze this together so that it forces it to go to the smaller side. So I want to small volume, high pressure. So here's the answer, letter D. Number 7, consider this equilibrium. Okay, delta H is negative. Delta H is negative means it's exothermic. That means heat is on the right side. And which change will shift the equilibrium to the left? Okay, so what have I got? I got 1, 2 moles of gas on the left. I have 2 moles of gas on the right. 2 and 2 means that if I do anything with the volume or the pressure, it will not make a change. Okay, so which will shift it to the left? If I add H2, that is going to be too much H2, shift to the right. If I increase the temperature, increasing the temperature, that will shift it to the left, so that's the answer. Okay, reducing the volume, because it's 2 moles and 2 moles will have no effect. Adding the catalyst will have no effect. And removing some HI will shift it to the right. Okay, so that's why none of those are the answer. Increasing the temperature will shift it to the left. Okay, question 8. What would cause the change in the kinetic energy diagram shown above? So what's happening? Here we have our dotted line. Okay, and that would be kind of like right here. But now that dotted line is more to the left. Okay, so that is a catalyst. We're looking for a catalyst, addition of a catalyst. Okay. Number 9, which of the following does not influence the speed of a chemical reaction? Okay, concentration of the reactants, well, that certainly will change speed of a chemical reaction. Temperature certainly will. Surface area of a solid, sure. Presence of a catalyst, that's sure. Okay, so the answer is E. None of these, all of these other things will change the speed of a chemical reaction. Number 10, what distance corresponds to the activation energy? So the activation energy is the energy to get from here to here. That's activation. That looks like letter B. Which point or points remain unchanged if a catalyst is added? Well, if we add a catalyst that lowers this hill, energy hill, okay, so that would change B, and that would change C, and that would change D. Those three things would be, which point or points remain unchanged? Do read carefully. Read unchanged. Okay, so the answer is A and E. A and E only. So the reactants and products don't change, just everything in the middle. Number 12, consider this system. The equilibrium constant expression is, so here we have a solid, that's not going to show up, and here we have a solid, that's not going to show up. So we're looking at something with concentration of H2O on the top and concentration of H2 on the bottom. It's 1 and 1 raised to those powers, so we're looking for something that looks like this. H2O on top, here it is, answer E. H2 over H2. Okay, 13 through 15. Now we're talking about this particular equilibrium right there. And it says that the KEQ is 285, so that's greater than 1. That might be important. And notice that there's a liquid here. Okay, so we have 1, 2, 3 moles of gas on the left side. We have only 2 moles of gas on the right side. And heat is over here. Those are all important points. So what's the equilibrium expression? Okay, well, because we have a liquid, we'll leave that out. So we're looking for something with H2 concentration squared on top, and on the bottom CH4 and Cl2 squared. We're looking for something like that. So H2 on the top by itself, so that's not the answer. This one looks good. In fact, that is the right answer. Answer B. Okay, this one's not because the Cl is not squared. This is upside down, and you have the two HCH2s, and that's not right. You know, those 2's are going to be exponents, not coefficients. Which of the following changes to the equilibrium would shift the equilibrium so more H2 would be produced? Okay, more H2 is produced. I always like to stop and say, okay, do I want it to shift to the right or shift to the left? If I want to make more H2, that's shift to the right. So which of these will shift this to the right? Okay, adding the catalyst, no, that does not shift it. Adding chlorine gas, okay, chlorine gas is on the left, that would shift it to the right, so that is a good answer. And removing CCl4 liquid, again, removing a liquid, okay, will not change anything. If you add or remove a liquid, that does not change. So the answer is 2 only, answer B. So keep in mind, adding or removing a liquid does not change the equilibrium. Okay, under which of the following conditions would we have the most CCl4 liquid when equilibrium is established? Well, we can, the amount of CCl4 can go up and down, so that's not a problem. And we say I want the most CCl4, so that means I want this to shift to the right. So I'm looking at what are conditions that will shift us to the right, and we're talking about temperature, and we're talking about volume. So what will shift it to the right? Temperature, here's the heat. So if I have high temperature, that'll shift it to the left, so I want low temperature. And the volume, because I have 2 moles of gas and 3 moles of gas, the small volume will shift it to the right. So I want to have low volume and low temperature, and that looks like answer A. Okay, the lowest temperature and the lowest volume. And that's that answer. Okay, 16. Which of the following is or are true at equilibrium? Okay, at equilibrium, the concentrations of the reactants and products are equal. We've decided no. That might be true, but it's not necessarily true, so that's not the good. The rates of the forward and reverse reaction are equal? Yes. Okay, and the reaction has stopped? No. It looks like it stopped, but it's actually things moving back and forth all the time. So 2 only, answer B. Okay, which of the following lists acids in increasing strength? Okay, so we have to look at these 3 numbers. Okay, the bigger the number, the stronger the acid, the more product favored it is. And of these, the highest number, okay, these 2 are bigger than the last one. So of those 2, the 4 times 10 to the minus 4 is larger than the 1.8 times 10 to the minus 4. And those are both larger than this. So these are actually in the right order. So we're looking for something increasing strength. So it should be this guy, then this guy, then this guy. So we're looking for HC6H5O2, which is less than HCO2H, which is less than HNO3, 2NO2. Okay, so it should end with HNO2. So that's not right, that's not right. Okay, the only one is this first one. And that's the right answer. Okay, for 18, 19, and 20, we're talking about this graph. So notice that we have a reaction of A turning into 2 B's. A turning into 2 B's. So this is A. A starts out high and ends up down here. And B starts low and goes up here. And at approximately what time is equilibrium established? Okay, equilibrium looks like it happens when we start getting flat lines here, so somewhere around 4 seconds. Okay, remember that that point doesn't mean anything. It looks kind of important, but it's not important. Okay, what's the value of the equilibrium constant? Okay, so a little tricky here. So the equilibrium constant, okay, is the concentration of B squared over the concentration of A. B squared over A. Now we just have to read the graph. B is 0.8. Just reading straight across. B is 0.8, so this is 0.8 squared over A, which is 0.2. So 0.8 times 0.8 divided by 0.2. I get 3.2 as my answer, and that is one of the choices. Okay, 19 is D. Okay, 20. If we started with equal concentrations of the reactants and products at equilibrium, what would we have? Okay, well, this is the equilibrium we're going to have, and it doesn't matter whether we start with all A, all B, or half A and half B. When we get done, it's going to look something like this. So the graph itself would look a little different. It would look like starting here, then it would go up to here and down to here, but the ending would look the same. So at the end, I would expect to have more B than I have A. So the concentration of B is greater than the concentration of A, or in other words, the concentration of A is less than the concentration of B. So the idea is I get to the same equilibrium, so just look at this chart and find an answer that matches that. So concentration A is less than B. Okay, for the free response, given the following reaction, A turns into B, okay, the potential energy of A is negative 70. So that's our initial point. The potential energy of B is negative 40. So that's our ending point. And the activation energy is 50. So starting from here, I go up 10, 20, 30, 40, 50. So that's my transition state. And what I'm going to do is to have a curve. And I'll draw it in green, so my curve goes like this. Okay, so draw the potential energy, label A, label B, label the transition state, and find E sub A and delta H. Okay, well, E sub A is this guy here, from the reactants to there, and then I'll label that E sub A, activation energy, and the delta H is from here to here. Okay, so B, what is the potential energy of the transition state? So what is the transition here at negative 20? So negative 20, those are kilojoules. Okay, we just read it off the graph. What's the value of the delta H? Okay, we're going 1, 2, 3, going up by 3. Okay, so the answer is positive 30 kilojoules. That's a 0. Try that again. Okay, and officially, what we've just done here is we say that's negative 40 minus negative 70. So negative 40 minus negative makes it positive. So that's negative 40 plus, that gives us the positive 30 kilojoules. So we can see it from the graph, uphill by 3 spaces, that's positive 30. Okay, this reaction is, I didn't almost miss that question. This is endothermic because we're going uphill. Okay, we have to put energy in to go uphill. So it's endothermic. I almost missed that question, so be careful. Okay, the kinetic energy graph at 40 degrees is shown. Sketch the graph and shade in the collisions that result in a reaction if the temperature is lowered to 20 degrees and a catalyst is added. So we're saying that this is a graph of 40 degrees. That means the center here means 40. So I want it to be at 20, so I'm going to move it over to 20. Okay, so I want it to be centered that way. So it's going to kind of squeeze my graph together. So probably taller and squeeze together like that. And I'm going to move my catalyst So I'm going to add a catalyst, which means move the threshold energy down, and I can move it down as much as I want to, just anything to the left of this line here. So I'm just going to move it over to here. Okay, and it says shade in the particles that are going to be able to react. So if I want everybody past the red line under my blue curve, so this here, so different people's answers can look a little bit different, but the idea is the blue curve should be centered 2 lines over, and the threshold energy is going to be moved over somewhat, and then color in the value. Okay, so that's my shading in the collisions that result in a reaction. Okay, my blue is the temperatures lowered, and the red line is the catalyst is added. And that's my answer. Okay, given the following reaction, okay, write the equilibrium expression. So say KEQ equals, okay, products of a reactants is aqueous, gas, and liquid. That was not going to show up in my expression. So it's just going to be the concentration of H3O plus times the concentration of F minus all over the concentration of HF. That's my 2 points. Okay, the values are, find the equilibrium constant. Okay, so they're giving us some numbers here. So H3O plus is 0.0134 molar. And F minus is 0.0134 molar. All over 0.25 molar. And so I'm just going to work out that answer. And for this I get 0.000718. Okay, and there were no units on that. So it's just 0.0134 times 0.0134 divided by 0.25, and I get that answer. At equilibrium, this reaction is, okay, this is definitely less than 1, so this is definitely reactant favored. It's a reactant favored question, equilibrium. Okay, 23. Given the following reaction, an experiment is performed by placing equal amounts of N2O4 and H2, so we're talking about those two, in a 2-liter container. Write the equilibrium expression for this. Okay, we can do that. KEQ equals, now that's a gas and a gas and a gas and a gas. So this, everybody's a gas, so everybody goes into the expression. So the products N2H4 and O2 squared all over N2O4 and H2 squared. Okay, that's my first 2 points. The value of the constant is 1.15 times 10 to the minus 9. That's very small. So this reaction definitely reactant favored, okay, because that is so much less than 1. How can we tell when the reaction mixture has reached equilibrium? Okay, we have constant observable properties. So I would say that, I'm going to say it that way. Constant observable properties. Or I could say that it looks like the reaction has stopped. Or I could say something like, the pressure remains constant. Or any other thing I could think of that I would be able to observe. But these are all, you don't know that, but these are all kind of colorless gases, so you wouldn't be hard to look at it, but you can measure the pressure. So some property about it remains constant. Okay, another experiment is conducted by placing equal amounts of N2H4 and O2 in a 2-liter container. So how does that compare? We were talking before about putting the first 2 chemicals in a container and letting it reach equilibrium. Now we're talking about putting the products in a container, and the value of the equilibrium is, it will come out to be the same equilibrium. Okay, if I start with my reactants or I start with my products, I'm going to end up with the same situation. And we saw that when we did the beaker, we could start with everybody in the product side, everybody in the reactant side. We get to the same equilibrium no matter what. And that is the whole test.